Hi, this is Team Garbage Pro. We are going to talk about 3D garbage image classification today. Our teammates are Ray Chen, Qi Wen, Ren Chang, and Hen Guang. Next page, please. So currently, world cities generate about 1.3 billion tons of solid waste per year. This volume is expected to increase to 2.2 billion tons by 2025. In addition, solid waste management costs will increase from today's annual $205.4 billion to about $375.5 billion in 2025. Next page, please. So we want to develop a model that could do 3D garbage image classification. As Bellow's guide, there are two mainstreaming approaches for applying deep learning on 3D point clouds. One converting 3D objects to 2D, and the other processing 3D directly. We find that the existing method of extracting features from 3D cloud point data has some limitations and would like to choose an image-based method which converts the 3D objects to sphere with sphere projections and apply them with the spherical CNNs. The main goal of this project is to project 3D images onto spheres with Gaussian mixture model and use spherical CNN space model for 3D image classifications. Next page, please.
Now let's talk about methodology. First, data. For this project, we use the 3D MNIST dataset in Kaggle to imitate 3D garbage images. The raw data from MNIST dataset is augmented from 2D space by proposing z-axis values based on intensity. Thus, the z-axis shares some correlation from the x and y axis. The entire dataset is stored as 4096D vectors obtained from the voxelization, where x, y, z are all 16. Here are two of the transform raw data samples. Next, please. Our proposed GMM and spherical CNN model is an image-based method. We hope to capture the shape attributes of the objects while achieving translational and rotational invariance. Apart from our proposed model, we also experimented with 3D CNN and some popular classification models, including random forests, logistic regression, and support vector machines. Random forest is a classification algorithm including multiple decision trees. Each decision tree in the random forest spits out a class prediction. And logistic regression and support vector machines might be the most popular traditional classification methods. Since our dataset has 10 classes, we have to consider the multi-class case for logistic regression and SVM. For the training, we apply one versus rest strategy for multi-class classification. As for the 3D CNN, a 3D CNN is a 3D-based method. It is simply the 3D equivalent of 2D CNN. Originally, a 2D convolution layer is an entry-per-entry multiplication between the inputs and the different filters, where filters and inputs are 2D matrices. In the 3D convolution layer, the same operations are used. We do these operations on multiple pairs of 2D matrices. Padding options and the slice steps option work the same way. Next, please.
For our own approaches, firstly, we would like to apply spherical projection just to convert a 3D object onto a spherical domain centered around this barrier at center. And there are actually two ways to do so. The first one is depth variation of a 3D object, which means ray tracing from each point on the sphere to the center. The second one is contour information viewed from the different angle. Next. Our approach, we would like to use GM-based projection. This one actually including two parts. The first one is the one we just introduced, the depth-based projection. And then it's just making the 3D to the S2, meaning sphere surface, to kind of reducing the dimension. And the second part is our novel part, is the GM part, meaning like we add a weight to each data point with Gaussian distribution as a neighborhood function, as you can see below the formula. And also we have a gradient as a hyperparameter to tune it. And after all of that, we can get S2 grid. With S2 grid values, we can create such feature map. You can see next. And this is an example of feature map for number 0. Next. When we got S2 grid, we can also combine it with the density map we created to get a spheres. Basically just multiple sphere in a sphere. we got this just for boosting our accuracy for the model. Next. After doing everything, we put everything into the spherical CNN, which also known as S2 CNN. Taco proposed this, and he, for as their paper said, they just did extending the normal CNN to the corresponding group of SO3, meaning 3D manifold. And they get kind of special GFFT for this, and just to make it less complex and to running faster. Next.
So for the result part, we evaluate the performance of the models based on testing accuracy, and we want to compare with our own method, with, for example, the support vector machine, or random forest, 3D CNN, and so on. So we can see from these pictures that for the 3D CNN, it achieves the accuracy of the 67%. And for other traditional methods, for example, the logistic regression has the lowest accuracy. It has around 58%. And for random forest, it has around 67%. And for our model of the GNM plus the spherical CNN, we want to compare two different data format. So the first is that we want to train the data with not rotated images, and we want to test it also with not rotated images. And later we want to test it, like training it in not rotated images. However, we want to test it with the rotated images. And we can see that the model of GNMM plus spherical CNN has a high accuracy among all of the traditional methods.
So talking about the future work, currently if most points are too concentrated in the 3D point cloud, then it will be pretty difficult to reflect outliers in the model and thus decrease its accuracy. Further actions are needed to take care of the outliers and group points heuristically in order to improve efficiency. We should work on a way to better represent the depth invariance, thus showing more detailed information about the shape of our object. For example, we can try to extract features based on each data point and collect projection of each data point onto the sphere as features. That's all for our presentations. Thank you very much for watching.